Yeah, so hello everyone. So today in this general lecture series, we will have Surya Gavva from City University of New York. He finished his PhD last year from Rutgers University. He was a speaker in the previous trimester, also speaking on the application of harmonic analysis in late September. Today he is planned to speak on the representation theory in complex forms. So over to you, Surya.
Yeah. Okay. Yeah. Thank you. Thanks a lot. It's always great to talk here. Uh, so the plan is to just, I guess the previous lectures you've been looking at the representations of SL to R, um, and in general, um, uh, kind of giving a description of the representations, irreducible representations. Um, yeah, trying to like uh, decompose the space of functions on like G, for instance. So now we'll see instead of functions on G, if you replace G with some other spaces like G mod gamma, for gamma, some discrete subgroup. Uh, there's a lot of number theory involved that comes up like based on the gamma that if you change gamma, or based on the gamma that you take, there's a lot of number theory that will enter into the picture when you want to do this decomposition. So yeah, so some basics. Yeah, so we have some fundamental objects that we deal with. So we have the upper half plane. It's just Z such that Y is positive, and there's an action of SL to R or PSL to R on H given by the Mobius transformations. GZ is AZ plus B over CZ plus D. So there's some calculations that you can do. Like if you want, you can compute that imaginary product of ZZ is basically imaginary product of Z by CZ plus D absolute value squared. If you compute the differential D gamma Z, it's DZ over CZ plus D squared. Okay, so these are, if you haven't computed these quantities before, like just computing these things, it's really helpful. So you see these quantities like 1 over CZ plus D whole squared, and even 1 over absolute value of 1 over CZ squared a lot of times in this theory. So just trying to, if you just compute, it's like you have an explicit expression, just compute the imaginary parts and also compute this derivative. So you can easily see that you have these quantities. And okay, so that's one thing. What else? So this space H, it's obviously it's a subset of complex numbers, so it has complex structure and so on. But it also is a has a it's a Riemannian surface. So you can have, in fact, with this metric dx squared plus dy squared over y squared, it is a constant curvature -1 space. So, and the mu z, this is the invariant measure on the space. And there are some quantities these are some quantities that describe the distance on the space. So anyway, so we'll so G acts on this H. So trying to understand or like more. So yeah, so the spectral decomposition on H or H mod some discrete subgroups is the theory of automorphic forms. So before that, so let me just so roughly automorphic forms or an automorphic function is just a function on some space such which is periodic with respect to some group, a discrete group, say acting on a space. For instance, just if you have an equation like f of gamma x is f of x for all these some discrete group, a group of discrete elements, a discrete subgroup of a discrete group acting on the space, then yeah, so you have all these equations, so periodicity equations. That f has to satisfy. Such a f is called automorphic. Automorphic is just a fancy name for periodic. So let's see. For instance, if you just like if the space is R and if the discrete group is Z, so you talk if function like e to the 2 pi I Z. or 2 pi x is a periodic function. So it's invariant under Z, right? And so you could call it as an automorphic function. And in fact, here this function is also an eigenfunction for this kind of a second order operator, the Laplacian. So we had R and Z. So instead of R and Z, we can take more other spaces that are important for number theory or geometry. For instance, you can take any Lie group. So think of, if you want to think of SL to R or SL and R. And then you can take some closed subgroup, for instance. So you can think of just SO to R or SO and R. And you can consider this quotient. This quotient is you can see that it is a Riemannian manifold, and there's an action of G on like G is G mod K, so there's an action of G on the space, and similarly, and you can take some gamma subset of G, which is a discrete subgroup, and you can again ask for functions which satisfy f of gamma x equals f of x. That's the automorphic part. In addition to that, we also tend to ask for f to satisfy some differential equations. So just take some.
So these differential operators are invariant with respect to the same group, with respect to the function is automorphic.
Yeah, the group. Yeah, so they commute with the group action. Yeah, so they're invariant with respect to the G action. Yes. So you take such differential operators.
We are thinking about the automorphic function with respect to a discrete subgroup, right?
Yes.
And but this the invariant of differential operators is with respect to some other group, full group, right? What?
No. So the invariance is just with respect to G, right? So for instance, in the case of, for instance, the Laplacian, what I'm saying is this delta f x plus Z is the same thing as delta f of x plus Z. Like you can translate and differentiate, or differentiate and translate, you get the same thing. So
delta is invariant of with respect to which group? R.
This translation. If T is T represents a subgroup. Yeah, it's the R action on
Okay.
Similarly here, you just delta. So F. So Gx. Let's say G is acting this way. So Gx. Okay, so in this case, Gx like this. So yeah, you want some equation like this. Delta of f Gx is the same thing as G. So G acting on delta of. So delta f at Gx. Yeah, so you just want delta to commute with the G action.
Okay,
yeah?
okay. Oh, yeah, okay.
Okay. Okay. So, okay, so more generally, okay, so I should have. So instead of just f of x equals gamma x, we also tend to put some extra factors here. So for instance, you can put some factors. It's okay to put some factors. Also, we'll see that later. So some chi of gamma or some extra factors times f of x. So this is like, so instead of asking for invariance of f of x, you would ask invariance of some, say, f of x dx to the KO2 or some other objects related to f. So invariance of those objects, like for instance, if you ask for invariance of f of z dz to the KO2 under gamma is different from the invariance under this of the function. So you'll have some extra factors. Okay, so anyway, so the notion of automorphic function is just some slight generalization of just a periodic function, and we all like just think of exponential 2 pi x periodic function, and so we also ask for the function to satisfy some we want it to be an eigenfunction of some nice differential operators. So let's see. In the case of R and Z, again, let's take the basic cases. So you want a periodic function just satisfies these equations. And so one way to think of it is just you look at the function on a fundamental domain. So for instance, you can take a function which is like x on from 0 to 1, and then just extend it periodically. So that is this fractional part of x function. It has this expansion and so on. So that's one way to create these periodic functions. But this exponential to pi n x kind of functions are eigenfunctions of these operators. Okay, so what else? So if you want to get some periodic functions, another way to get, instead of just taking the fundamental domain and just looking at some function and just saying that it looks the same on every fundamental domain or every shift, you can also say that okay, take any function f and average it over the group. That is just translate that function, say f is sufficiently decaying function, small, like then. So you could ask something like, just translate that function with these integers and then add them. So, and consider this new function. You can now see that this new function is invariant under, so g of x plus 1 is g of x. So because you're averaging under the group action already, so you'll see that under the group action, it is invariant. So this is another way to create periodic functions. Okay. So again, this is the case of R and Z already. It already has a lot of interesting features. So for instance, for R and Z, so one of the most important identity about this embedding of how R sits inside Z is this thing called Poisson summation. If you sum over some nice function, sufficiently smooth and decaying function f over the integers, it's the same thing as sum of the Fourier transform defined this way of over the integers. Okay, so this is easy to prove. You compute trace of certain functions. Yeah, so but it's not hard to prove. It's just you can, let's say, just some kind of trace calculation, or just consider f of x plus n sum and just compute the Fourier transform of this. You can easily see this identity. Okay, so why is this helpful? So for, at least for analytic number theorists, it's really helpful, and it's probably one of the most important tools. So for instance, so if you plug in some important functions, like for instance these Gaussians. So Gaussians are all like, so for instance, when t equals 1, e to the minus pi x squared is its Fourier transform is exactly e to the minus pi x squared. This so you can have some extra parameters, and you'll see that for e to the minus pi x squared t, there's a Fourier transform that looks like this. So if you use such a function, a special function, basically a Gaussian, you'll get some identities of an identity of this form, and this identity is basically an identity for the theta series. Okay, so this and it helps. So once you have that, it helps you to, so theta series is this series e to the 2 pi n squared z. Okay, so you can see that you can get some interesting relations on theta z. In fact, you can prove that theta z is a modular form of some kind. So this relation between f and f hat, and the fact that f hat is quite similar to f, gives you relations on theta z. So that's one of the first times this idea of modular forms. The first instances where people found some modular objects. Okay, so Yeah, so I'm slowly trying to build to the classical modular forms, and what I'm saying is just do the standard Fourier analysis on with R and Z, like R in R mod Z, and then you have this identity, which is some kind of trace identity. It's easy, quite easy to prove in this case, and that if you specialize it to some functions, helps you to get like some functions which are modular. So also this identity here is also equal if any of you are interested. So is also equivalent to the functional equation of the Riemann zeta function. So there's a relation between zeta s and zeta 1 minus s. So that's also is equivalent to this Poisson summation. Okay, so that's one first time people saw some source of modular forms. And next, there are other places. So for instance, instead of looking at Z inside R, now you can also take any lattice, like inside the complex plane, some lattice generated by W1 and W2, and you can consider some functions which are invariant under this action by the lattice. That means that the fundamental domain is just some parallelogram inside the complex plane, and by any so f of z plus any of these, if you translate by any lattice element, the function is constant. So it's periodic in two directions. So such functions are called elliptic functions. And for instance, you can, by this idea of averaging that I talked about, like it might, so you can just average over all. So you can create some functions. So it's basically by averaging over all, like this is an average over this action of the lattice. So by just this kind of averaging operation, you can create these interesting functions. Like, so these functions, for instance, this function I wrote here, it's called the Weierstrass function. And if you take the derivative, you get some other sum over this lattice. And if you compute a little bit, you're going to see that this function has some interesting expansion with some constants that,
They're eigenfunction of which operator?
Okay, so let's see, I guess I should not, so these are not really, so these are not, so these are not eigenfunctions. So I'm just trying to build up to some modular forms. Here,
So
these are not eigenfunctions.
So is there a condition when something would be eigenfunction or when something would be not?
So in this case, like, right, in the C mod lattice case, the eigenfunctions are again, this is like R mod, like it's either 2 pi I and M X, like two copies of it'll be just two copies of things, right? So it's just C is just, we are not using anything about C that much, so it's just R2. So but here somehow so okay, so these are not really these are just periodic functions. These are not functions as such. Like they don't have just one Fourier coefficient. They have a lot of Fourier coefficients. So
but they are automorphic with respect to a lattice in the R2.
So they just so they don't they're automorphic with respect to the lattice. It's just that they don't have this differential equation conditions. But like so here I'm not
okay, we'll see.
So anyway, so so I just build these functions by just averaging over, summing over the lattice, because it's sum over the lattice. If you shift it, you'll get back. I mean, so right, is that clear? So if you're in some sense, this is already a sum over lattice. Even if you shift it, that particular element exists inside the sum. So it is it's easiest way to. Okay, is the share stopped?
It is there. Don't worry.
It says it's paused for me.
It might be paused if you move the and from the other side we could not see.
I'm moving. Can you see it?
No movement.
Okay, so I guess it's okay. So something happened. Why is it paused? Okay, so let's see. Can you? Uh, okay, share. Yeah, sorry. Um, yeah, so uh, yeah, so these periodic functions along two directions helps you to create some interesting functions. So for instance, as a function of the lattice, so you can find, so if you, so you, these elliptic functions, if you expand and there are some of the coefficients of this Taylor series are these functions, G functions, GK as functions of the lattice. So every lattice will have different constants. So for a fixed lattice, they're fixed constants, but the constant depend on the lattice. So now if you think of this constants as functions of the lattice, right? So this is a constant that's a function of lattice. These functions are modular forms. Okay, so this is one. So we'll talk more about it, but this is one case where we one was historically when we found modular forms. So the way to think of these things is this. So let's see. So if you have, so how do you parameterize lattices, right? So lattice, you have, if you have a basis of like if you have a lattice, I'm calling them gamma. So this lattice, how do you parameterize it? So let's say I assume I can interchange them, and I can assume that the imaginary part of W1 over W2 is positive. And then, in fact, after scale, so if I'm okay with some scaling, I can imagine that my lattice actually looks like this. So one of the basis element is 1, another basis element is Z. So now I can think the lattice generated by these 1 and Z can be thought of as yeah, so we got, so, and Z belongs to the upper half plane. Okay, so uh yeah, so the one way to parameterize lattices is just through up to lattices with up to scaling and some rotations is to just as a point in the upper half plane. Okay, so the way what I'm doing is, yeah, instead of taking W1 and W2, I just scale it back and I take W1 over W2 and 1. Okay, so I parameterize it by this number Z and 1, and then you can ask, does just will different Z's give you different lattices? That's not the case, because you can have let's say yeah, so there are, you can do some change of basis, right? So two different bases can give you the same lattice. For instance, two bases which differ by this made like some linear change of variables where that with integer coefficients where the determinant is plus or minus 1 will give you back the same lattice. So the lattice is not uniquely determined, like each lattice will have different bases. So you should quotient, like if you want to parameterize the space of lattices, you should quotient out by these different set of bases that you can have. So okay, so long story. So what ultimately what happens is that if you parameterize your lattices by 1 and Z, like up to scaling and rotations, all the different bases are related by Z going to gamma Z. So gamma is an element in SL to Z. Okay, so it means Z and gamma Z will generate the same lattice. Okay, so that means it's not the entire Z's that give you lattices, it's just so Z is in upper half plane. So so you should quotient out by this SL to Z to get to actually get the space of unimodular lattices. So anyway, so one way to think of the space, this H mod S set to Z, this is something that is the space of lattices. Okay. So okay, so let's see. Now like I said, take any. So if you have a function on the lattice, this C mod gamma, an elliptic function, a function which is periodic with respect to the lattice. And let's say it satisfies some extra properties. So f of so W1, W2 are the basis of the lattice, and then U is just a coordinate, like the coordinate, or Z is the coordinate inside the complex plane. And if the function satisfies this, it's some homogeneous properties, let's f of lambda U, lambda W, lambda W2, if it comes out as some lambda to the minus k, it's just some, it's an analogous to some homogeneous polynomials, right? If you have xy plus y squared, you scale it with lambda, you get a lambda squared. So if you can get somehow, if you have a function which satisfies up when you scale it with lambda and each of these coordinates, if lambda to the minus k comes out, so that's how somehow it's like degree minus k. So you can, so by in terms of these descriptions, so you can think of this function that we have as a function on H mod gamma, or basically H as a function that satisfies f of gamma Z is this some interesting factor CZ plus D to the K times f of C. Okay. So instead of just f of gamma Z equals f of Z, so if you you might, yeah, so depending on the problem here, in this case, if this comes from some homogeneous functions on this C mod so C mod gamma corresponding to an elliptic function, you get some relation like this. Okay. Okay, so as I said, these quantities that we saw before, the gk gamma, are they're functions of gamma, and like, okay, so functions of the lattice. Now, if I actually represent them as functions of, as I said, lattices are, I'm describing them with Z in H. So that's, so the way you think of it, the lattice is the lattice generated by 1 and Z. Okay, so if with that identification, so my lattice is, so every lattice I denote it by this point Z in the upper half plane. So with that identification, this function that we saw before will become a function like this. ZKZ is mz plus n are like the, so because it's mz plus n1, these are all the lattice elements in the lattice. So it becomes a sum like this, and you can check that this function, right? So this function now will have this property. So zk of gamma z under the action gamma z is az plus b over cz plus d is not just zz, but it has the extra factor cz plus d to the k. Okay. And such objects, such things are called Eisenstein series. So these zkz's are called Eisenstein series. And yeah, you can expand them in terms of there are other expansions of the Eisenstein series, which and have some interesting arithmetic coefficients that show up if you expand them. So again, so all of it is coming from, yeah, so simple averaging over the lattice helps you to such is the quantity, and as a function of the lattice, it's going to give you that whole quantity as a, like, so these quantities that are computed as a function of the lattice has some nice, interesting invariant properties. So this action by SL to Z, the gamma, you should think of it as like change of, so SL to Z, just when it acts, it's just changing the basis of the lattice. Okay. So yeah, so there are this, you can normalize those instead of standard this expressions that I wrote, you can normalize them to a little bit, and you can okay. So that's for normalized Eisenstein series, and more. So we have this lattice, right? So C1, so let's say W1, W2, or 1Z, whatever. So this the quotient space C mod the lattice is an elliptic curve. So that's an elliptic curve. And see, these are really important objects. And you can see that if you, the elliptic curve satisfies some, there's an equation like this. So we saw all these functions before. So these are this is a derivative of Weierstrass function. These are some quantities. In fact, these are the Eisenstein series, G4 and G6. So in terms of these quantities, this elliptic curve satisfies this equation. So this is like y square equals some 4x cube minus some plus ax plus b. So these coefficients here are functions of the particular elliptic curve. And if you have seen this quantity called discriminant before, the elliptic curve has a quantity called discriminant, and the discriminant, if you compute it in this case, will turn out to be this G2 cube minus 27 G3 squared, which is, again, that's a quantity that depends on the lattice. Okay, so now, so this quantity G4, G6, and even this delta, all of them satisfy these automorphic properties. So all of them are, so as such, the way we have seen them, you can see that all of them, so for instance, GKZ is this formula, you can see that this is like it's holomorphic, like or maybe it's not clear it's holomorphic, it's at least meromorphic. They're all nice analytic, complex analytic functions. Okay. So we have, so by just simple arguments, we have these different quantities which satisfy f of gamma z is f of z up to some extra factors. Here in this case, it's cz plus d to the k. Okay. So any questions about
these lattices are generated by certain sort of periods, right?
Yes. Yeah. So these W1, W2, like, so what I'm saying is every lattice is like this, right? W1, W2. I'm just up to scaling is the same thing as 1, comma z, where z is in the upper half plane.
But the W1, W2 are certain integrals of some functions, right?
Oh yeah. I mean, if you no, in the sense, yeah. If you give me this space C mod, this lattice, I can write this W1, W2 in terms of some integrals on that space, on the quotient space. This is, yeah. But right now we are thinking of it as a lattice. So yeah, they are just two.
No, W1, W2 are certain spatial integrals of certain spatial functions.
Yeah. So
coming from probably the Legendre differential equation, right?
Yeah. So if you can retrieve these lengths or whatever these numbers by integrating some functions on this on C mod term.
Now, if we take a bit more general differential equation and compute the periods, I mean under certain conditions, so we will get a different type of lattice maybe.
Yeah, I don't know what that. Yeah, okay. Yeah. So
what is called complex torus or maybe.
Yeah, we'll talk about it. I didn't
Okay.
really get that. Yeah. So so anyway, so okay, so I guess this is all I'm trying to do is motivate how this modular forms came up. It's just that there are these simple functions on space of on lattices, uh, like that come up when you write down some basic simple interesting natural functions by averaging over the lattice, and those functions as the function of lattice, like as the function of you can as the function of lattice have these if you look at their properties, what they're doing under change of basis. So the
What I'm trying to
acting like,
see is that modular group works well with this kind of lattices and this kind of
yeah. So because
elliptic
so what
curves, but which are
because
parameterized by the upper half plane.
yeah,
But where
exactly,
are the
because
other discrete subgroups in the SL2R, which are not commensurable with the modular group?
so they don't, you don't have such descriptions. Yes.
So then
Yeah.
you may also have, they also act on the same points which are parameterized by elliptic upper half plane, right? So what are the function theory related to those actions? Anyway,
So you can do, you don't need to, we don't have this description of H mod gamma. We'll just we can study them intrinsically, but so I'll come to it. But so this is the first introduction, the historical
yeah, I
introduction.
understand. Yeah. Okay,
So
see.
so the f so so so
I have
these are
one question.
functions on
Hello.
yeah
I have one question. You had explained that automorphic function is defined as f of gamma g equal to f of g, and the periodic function is f of g plus n equal to f of g.
So
Okay. So the question is, in case of periodic function, it is clear that f of z plus n is the period. Okay. So then for f of automorphic function f of gamma g, what is the period then?
Oh, so periodic. So in the sense, periodic just means that, so it here n is any number. I don't mean the period of the period. It just, so instead I'm talking about all integers, right? So the period is 1. So f of z plus 1 is f of 1, right? F of z. So in fact, if you write these equations, a lot of times f of z plus any number is, and I don't, by n I don't mean a period. It's just any number. If the period is 1, like I'm taking z.
No, that I got it. F of g plus 1 is equal to f of g, then 1 is the period. If I can take any number for n, then the n will be corresponding period. But my question is, for automatic function, f of gamma g equal to f of g. So the automatic function is also a periodic function, or what it can be called then? If it is periodic, then what is the period?
Oh, so periodic in the sense that it, So for instance, like, so right, so you have all these discrete ABCDs, which are gammas, for which you have this equation f of gamma z equals f of z, right? So in the sense, it's not just, you can't, and you can generate, I mean, in fact, maybe I'll show that. So this SL2Z, right? So this f of gamma z equals something, something. So in fact, you don't need to, these gammas are generated by these two particular matrices. So you can think, so you can just, instead of saying that it has periodic under all those gammas, you can just say if f of tz is something, f of sz is something. So you can say that these are like two different, if you want, I guess that's what, like instead of just one kind of a period, you have like, it's periodic under these two kind of actions.
Okay.
If you want. Okay. Yeah.
Thank you.
Okay. So anyway, so where are we? So we have H mod gamma, H mod SL2Z, which means it's or like H is Z and H represents this lattice, and SL2Z is basically change of variables or change of basis of the lattice. And so there's the natural action of SL to R. Okay, so to know something about this, so for instance, Z is sitting inside R, we know the fundamental domain, right? It's just 0 to 1 or something. So how does the fundamental domain here look? So I somehow this thing, okay, sorry, it didn't print, but I printed it in the last minute. So the fundamental domain looks like this. So this is the fundamental domain for this is SL to Z. So for these matrices A, B, C, D acting on H, this is how the fundamental domain looks like. Right? It's a real part X is between -12 and 1/2, and the absolute value is greater than 1. Okay, so now we saw these functions and we just study them all at once. So f of gamma z, so things we saw, these things like Eisenstein series and so on, so all of them satisfy this equation. Instead of just f of z, they have this extra k. So we want to understand all these functions which satisfy this equation. So like you take any k greater than or equal to 0, you can ask for functions that satisfy those equations. How do they look? In fact, then you can in fact check that the functions that we saw before, in fact, in some sense, generate all these functions. So in fact, if for instance, if you multiply two functions, so if f is a function which has this k is called the weight of the modular form. So if f has k and g has L, if you multiply f and g, then you can see that when you for the multiplied function, you get the weight will be k plus L. That's obvious from the definition. So so this mk times ml is will be inside mk plus L. So and then you get, so using some basic complex analysis arguments, so you need to do some basic counter integration on this fundamental domain. You can prove that, yeah, these are all the modular forms that you see. So if you want holomorphic functions which satisfy that equation, you can see that all the functions will be of this form. Either the function we saw before, this Eisenstein series, and the Eisenstein series, or maybe the square of the Eisenstein series, or multiplying these Eisenstein series, or yeah. So in fact, so all the functions will be just some polynomials. So this whole ring of modular forms, in fact, is a polynomial ring in these two Eisenstein series we saw before, G4 and G6. Okay, so that's okay. So all of them are with respect to SL to Z inside, sitting inside H, SL to R, acting on H. So that was, and the functions were all like holomorphic. Okay, so but now we can ask for more general settings instead of SL2Z. What happens if I take, so the nice thing about SL2Z is that this space H mod gamma, this fundamental domain, has finite volume. It looks like it's infinite, like it is extending. It's a big cylinder kind of a thing, but as I said, the metric is dx squared plus dy squared over y squared. As it goes up, there's a y squared in the denominator. So if you compute, so the measure will have dx dy over y squared. So so although it in the standard Euclidean sense, this is of infinite volume, but with respect to this hyperbolic measure, it's a finite volume. Okay, so this H mod SL2Z is finite volume, and it's acting discretely on H. The SL2Z is acting discretely on H. So in general, you can ask, oh, I want finite discrete subgroups acting so that I get finite co-volume. And this was such groups are called Fuchsian groups. And you can study automorphic forms with respect to those groups as well, so if you want. So in fact, yeah, so in fact, a lot of Riemannian surfaces, hyperbolic surfaces, like all hyperbolic surfaces can be written. So like if it's the surface hyperbolic, all of them can be written as H mod gamma for some gamma. And if it's compact surface, or if its surface is nice enough, the gamma will be such a nice discrete subgroup. Okay, so in fact, so you can study any discrete subgroup so that the volume is like just all you want is the H mod gamma is a finite volume and so on. But so if you're a number theorist, or you're interested in the specific subgroups of SL to Z, which are also finite co-volume. These are matrices ABCD, which satisfy this extra, so some congruence conditions. So this is equal to identity mod Q, or equal to upper triangular mod Q, or these unipotent elements mod Q. So okay, so these are some specific subgroups that are interesting, and so they appear a lot in number theory. Okay, so but in general, you can just study any instead of, so just if gamma is these gamma Qs that I wrote before, or any gamma that you have in mind, you can just study this equation. So f of gamma Z is Cz plus d to the k times f of z. You can also throw in some extra factors here. These are called multiplier systems. So I guess, yeah, so I'm going to skip that. But yeah, instead of, so for instance, in the case of gamma q, you can write some equations like f of gamma. So for instance, in the case of gamma naught q, you can study forms which satisfy f of gamma z as f of z, cz plus d to the k, and this extra factor chi of t, where if gamma is ABCD, you throw in this extra factor. Why is that helpful? If you have seen some theta series and so on, yeah. So these extra factors come up, but so for now it's okay if you. So for instance, yeah. So like there are some interesting functions where. Okay, I'll skip this as well. So instead of just CZ plus D, you'll have these extra factors. So I've written on the factors here. Like in the case of a series like this, it's called a theta series. You have the factor which looks like this. This is also some interesting number theoretic quantity. It's an extension of Legendre symbol, if you have seen this before. So yeah, so in general, again, it's f of gamma z, f of c, the cz plus c to the k, and some extra factors. Okay, so yeah, so people have been studying this, or they would change this gamma, they would change this extra factors here. So what are the parameters that you have? You have the gamma, that's the parameter of which it tells you under what action are you periodic. We have this k, which is coming as it's called the weight of the form, and this extra multiplier system, the extra factors that you have. So there are all these factors. People were studying them like in different contexts. They saw them, and so they would study them differently, like and so on. Okay, so okay, so before I move further, so there's one important property. So for instance, for many of these holomorphic functions that we saw before, so this, for instance, E4Z and so on, you can write down these expansions. So these are called the Fourier expansions of this series. So you'll have some interesting arithmetic coefficients. For instance, this particular function delta z, this has a formula in terms of E4 and E6 that we saw before. If you write down the Fourier expansion, so this is the weight 12. So the delta of gamma z will be Cz plus d to the 12 times f of c. So for this particular modular form. It's a weight-12 form. You can see that the constant term, there's no n equals 0 term. The zeroth Fourier coefficient is 0. Okay, such forms are called the cusp forms. Okay, and they're really important. We'll see later, but just as seen right now, it's just that the zeroth Fourier coefficient are 0. So you can write down. So yeah, so you instead of so there are these special functions that you can write, which helps us to understand the space of modular forms. They're called Poincare series, and there. And then if you write down their Fourier expansions, you can see some interesting quantities. They're called the Kloosterman sums. If you haven't seen them before, these are some exponential sums, which modulo C. So
Kloosterman sums comes from the Poincare series?
yeah, so you write the Poincare series and look at its Fourier expansion.
That makes the Kloosterman sums.
Yeah. I mean, yeah, so the somehow, yeah, the Fourier, like the Fourier expansion.
This Poincare series for the full modular group you're talking about.
Yeah,
SL to Z.
I mean, yeah, this is this is for the SL to Z. Yeah. So if you change the group, you'll the.
I mean, if you take the congruent subgroups or some other subgroups, then.
Yeah. So they will have essentially Kloosterman sums or quite close to the standard Kloosterman sums. If you change the group completely, you'll get some other exponential sums, but which they might not be arithmetic. I mean, like that nice. Like in the sense you might not be able to. Yeah. So for instance, these Kloosterman sums are so nice. These are exponential sums. There's like in the sense they look like e to the mx plus nx bar over c. Okay. X mod c. So it's a e to the 2 pi I. So this is a sum of approximately c terms, but you can prove that this is of absolute value at most square root c. So it has a square root cancellation, and yeah, so these are very nice. So so and a lot of number theory goes in to prove such fact that you have a sum of c terms is only of absolute value of square root c. So yeah, but that such things and to prove such facts, it depends on sorry, it depends on arithmetic. So it's SL to Z is really important. If you take some other lattice, you'll have some other sum, but we can't. The sums won't be some nice arithmetic things. Okay. So in general, like you can write down some kind of a trace form. So you take you can take the basis of like say of these forms. In fact, like the cusp forms, for instance, you can write some formula called a Peterson trace formula. It just follows from this Fourier expansion for the Poincare series. So you get formulas like this which relate the Fourier coefficients of modular forms with these Kloosterman sums. And this is really, if you're an analytic number theorist, this is really important. In fact, for instance, you can get a formula for like just because weight 12 forms, there is only one, it's a dimension 1. There will be only one term on this side, and that one term essentially can be made to be equal to this tau of n, which is the Fourier coefficient for the delta z. And then you get a formula for delta tau of n in terms of the Kloosterman sums. And this is helpful to get bounds. If you want to, yeah. So for some reason, understanding what is the size of tau n is really, really important. And like these can show up in some equidistribution problems. And yeah, so a lot of number theory problems, like bounds on these quantities will mean, like a good bound will mean that you're proving some equidistribution or some sort of nice properties of nice properties. So yeah, so such a trace formula helps you to get explicit formula for these Fourier coefficients, these arithmetic coefficients. And one, like in this particular case, these closed domain sums are some things that we know pretty well. So we can get really good bounds on this tau n. So, but okay, so but yeah, if you want to do it explicitly, but by Deligne and some high-fi machinery, you can easily prove that tau n is at most n to the 11/2. That's epsilon. Okay, so okay, so again, so we have these functions. Let me repeat. So f of gamma z is f of z times some things, and we write some Fourier expansions, and if the Fourier expansion, the quotient and zeroth coefficient is 0, it's called a cusp form. And sometimes the Fourier coefficient seems to have some very, very non-trivial properties. For instance, for this series that we have seen before, again, I was talking about before, you can see that they have really, really interesting multiplicative properties. Tau of m times tau of n. Let's say if m and n are co-prime, is this tau of m n. In general, there's a formula like this. Okay, so how do you, so this was observed by Ramanujan, for instance. How do you prove? But how do you prove such a formula? Okay, so to prove such a formula, okay, so it was observed by Ramanujan, but it was proved by Mordell. So Mordell was the one who proved such a formula. For that, he introduced these operators called the Hecke operators. So these are operators that act on these modular forms. There are some averaging operators. So I'll just so for every n, there's an operator and they act in a certain way. So they're averaging over these cosets. So, but anyway, so these operators preserve these spaces of modular forms, and they commute. For instance, T and the commuting operators. So from these extra operators that we found, like on the space, like, so if you apply, for instance, you have this f of z and use the fact that this space is one-dimensional, hence the f of z has to be an eigenfunction for all these operators. Okay, it's not only satisfying this periodicity properties, it's now an eigenfunction for these interesting arithmetic operators. That helps you to prove like these operators have these commuting properties, and that helps you to prove these the multiplicative properties for these Fourier coefficients. So in general, okay, so we have these operators, the Hecke operators, Tn, and they're acting on our modular forms, and I said they commute, so we can find a space, a basis of eigenfunctions for all these operators. So they simultaneously satisfy Tnf as some lambda of n times f. Okay, so not only they have this automorphic relations, you get these extra relations that they are some eigenfunctions. Okay, so let's see. Yeah, so there's this notion of new forms. Sometimes forms on lower levels, forms on like a lower level can induce a form on higher level by just so if you take f of z on a lower level by just taking f of some constant times z, that we can see like is a modular form on like a level higher. So yeah, so in that sense, things coming from lower levels are some kind, we think of them as some kind of old forms. So so forms which are orthogonal to these are called new forms. So these are genuinely new objects inside these spaces. So, okay, I'll skip this. So yeah, I'll skip this as well. So once you have this, so these new forms, this AK, this functions which satisfy not only these automorphic properties, they also satisfy these eigenfunction equations as eigenfunctions of the Hecke operators. Then you can see that once you start with such a function, you can write something called an L function for the function by just putting together like some sort of generating series for the Fourier coefficients. And the L function has really, really nice properties. These are objects that are of, if you remember, they're really, really important objects. So for instance, the Fermat's last theorem is proved by showing that a certain series attached to an elliptic curve called the Hasse-Weil L function is in fact comes from a modular form. So a modular form on this gamma q, in fact, a weight 2 modular form. Yeah. Anyway, so this is the Tanya-Mashimura Weil theorem. Weil's, sorry. Okay, so why are these? So L functions are helpful because sometimes it's not easy to realize that some function is automorphic. These relations, right? How do you prove that all these relations are true? So instead of proving relations explicitly that it is automorphic, that proving all these periodicity relations, we are somehow doing it in a transform space. LFS is some kind of a transform of F, and these relations will correspond to some kind of the automorphic relations here will correspond to some relations on the L function side, and sometimes it's easy to just establish those relations and then go back. So these are called converse theorems. So once you establish that the L functions themselves have some nice properties, you can prove that F itself is a modular form. Okay, so I'll skip this as well. Okay, so the forms that we saw till now came from these Eisenstein series or in general some holomorphic forms which satisfy some equations. Okay, but later Hecke and Maass were studying some other kind of L functions attached to some quadratic fields. So Q square root D, Q square root minus D. So just there are some generalizations of the Riemann zeta function. When they were studying these, they realized that they constructed, okay, I'll skip this as well. They constructed some attached to these objects on quadratic fields. They found some other functions, capital F of Z, which are not holomorphic. They're not holomorphic. Okay. And they satisfy slightly different period conditions on the automorphy. F of gamma Z is this, like for instance, in this case, instead of CZ plus D to something, it's CZ plus D over absolute value CZ plus D. The factor is slightly different times F of Z. So these are some real analytic. This is a real analytic function which satisfies this slightly different automorphic condition, and in fact they also satisfy some extra differential equations. In fact, they satisfy so this operator on H, which is like the Laplacian, which is the weight 1 Laplacian. It is an eigenfunction for that Laplacian. Okay, So it just, he was studying these generalizations purely from arithmetic point of view. And he constructed some functions, f of z, and then they turn out to have properties that are different from the standard holomorphic functions that we saw before. So, and so they are called Maass forms. So what are, like, for instance, another example of such forms is what is called a null holomorphic Eisenstein series. It's also obtained by some set of averaging, imaginary part of gamma z to the s. So we average gamma with this, but the function that you're averaging is this imaginary part of gamma z.
Surya, we need to stop also, maybe in 5 minutes.
Okay, yeah. So yeah, fine. So let me, I guess I didn't get to, okay. So anyway, so there were these modular forms coming from one kind of source, and then people realized that there are these other real analytic functions which satisfy some sort of automorphic properties, but they also satisfy some these differential equations with these operators like Laplacian. Okay, so these are called Maass forms now. Okay, so these are called Maass forms. So which are also objects with some automorphy, and they are also satisfying instead of, so you can think of holomorphic functions satisfying a differential equation like it's not depending on right, Cauchy-Riemann equations, right? Holomorphy means they're satisfying Cauchy-Riemann equations, but these Maass forms are satisfying some of the equations. They're like eigenfunctions of these Laplacian. So both of them are solving are solutions to some differential equations. They are also have some automorphy conditions, and so you also impose some extra conditions like polynomial growth, so to avoid. So yeah, to avoid so some other class of objects. So if you restrict the growth, if you say that the functions don't grow too fast, so you get these functions. Okay, so they're called the Maass forms. So they satisfy. So for instance, the Maass form of 8K satisfies this equation, satisfies this differential equation, and it's as it goes to infinity or like cusps, it doesn't grow that fast. Okay, so things are called Maass forms. So both of them, so we have these two objects. So how do you understand these objects? Okay, well, so one of them are solving one kind of equation, like the solution to one kind of equation, and other things are solutions to other kind of equations. How do you understand all of these in one shot? So the common thing is that, so for instance, even the modular forms that you have, like start with f of z, if you multiply with this factor of y to the k over 2, you can check that this is a Maass form. Okay, modular forms satisfy some other relations, but when you multiply with this factor y to the k over 2, this now is going to satisfy, this is a Maass form. Okay. Okay, so let's see. And you can try to write down okay, so for the Maass forms, you can try to write down some Fourier expansions. These because these are not holomorphic, the Fourier expansions won't just look like e to the 2 pi n z. They will look, for instance, like in the case of Eisenstein series, you have these like special functions, the best k Bessel functions, right? So, okay, let's see. So the k-Bessel functions are related to what are called the Whittaker functions. Again, so all these functions are, so you see a lot of special functions that appear. Okay, I'll probably skip. So again, those special functions are related to, so what you've seen in previous lectures when you were studying Planck theorem and so on for SL2R, they come up, like for instance, there is this C function of Harshvardhan that shows up. Okay. So I'll go to the last. So the point is, so all of these things are functions on H mod gamma, but there's a way to lift. You can, so H is not, so as I said, H, you can identify H with G mod K. So functions on H can be thought of as functions on G. So you can lift all these functions that we talked about to functions on G. So we can think of them as functions on G, invariant under gamma. So they are functions on G mod gamma. Let's see, the functions on G mod gamma. And so now, so all these different properties that we saw before, the Maass forms, all the conditions about the CZ plus T to the K, etc., all of them now can be framed in terms of representation theory. So for instance, the weight can be thought of as like as the K type, like understand. So the action of a subgroup of this SO2, the weight corresponds to, like the weights K correspond to the characters on this SO2 and so on. Yeah, so the point is once we have these functions on H mod gamma, which we now think of as functions on G mod gamma.
Perhaps we wrap it, man, here.
Sorry?
Perhaps we wrap it here because it is a bit subtle would be to representation theory you are starting to talk about. Maybe you take up next talk.
Yeah, so I'll talk in the next talk. Yeah, but the point is, all these special functions that we saw before, all these and the fact that you get different kinds of, so some really special like all these Whittaker functions, K Bessel functions, and so on. Also so there's a unified way to see all these things, and that like once we see them through the viewpoint of representation theory, just things you can conceptually explain, like for instance, all these differential operators, like you can explain them in terms of the group and the representation theory of the group. So I'll get into that in the next lecture, but like, so it just, I guess, so this lecture is just, you have all these different kinds of modular forms, and somehow they look very, very different, but this, like, how do you explain that these things exist, and how do you explain them from the point of view of the group? How does SL2R see all these things? Okay, yeah, so I'll do that in the next lecture, I guess, yeah. Okay.
Thanks, Surya, for a very engaging talk actually to all throughout and but having so much material to finish it.
Yeah. So I guess I should have wrapped up this thing before, but anyway. Yeah.
So anyone has any questions? Hello, Professor Ravi.
Hi.
Your voice is, we cannot hear actually somehow. Somehow your system do not have voice, perhaps. Unmute again, maybe. You are muted, Professor Ravi. No, not. It's some technical problem in your system, perhaps. Yeah, now it is connecting, perhaps. Not yet. Okay, he will give another talk next month. So you can join there.
Yeah.
So anyone else have any questions? Probably no. So you start from this slide maybe next talk.
Yeah.
I had this question like, so the way things, since I'm interested in the subgroups, which are more general than the modular group. So what are the kind of objects they are parameterizing, and what sort of this functional analysis comes into the play? So
So
you understanding
mean,
that?
yeah, you can do the spectral theory like normally, like in the sense, like you have.
So like co-compact Fuchsian groups correspond to
So
Shimura curves. So how this function theory would be look like there? So they parameterize certain abelian varieties. And they would be also. Yeah, now he is able to speak. Yeah, go ahead, sir. It is still not working well, actually.
So the spectral decomposition, so this, like for if the co-volume is finite, the spectral decomposition is quite, I guess, I mean, you have the decomposition once you have some analytic properties and so on, but it's just that, so what do you do with it? Like, so what is the question? So you're saying, so what was the question exactly?
So my question were from beginning. So your periods of the which generate the lattice. Those periods are integral numbers of certain integrals. Definite integral.
Okay.
On
So
certain domains on the sphere, you can say P1 minus 3 point. So if you change those differential equations more general, as far as I understand, those are the elliptic integrals.
Okay.
And if you move to more general integral, which have the integrand is higher degree polynomial. For the elliptic integral, the integrand had certain polynomials, radicals, which are in 3 degree, right? So you will get certain period, and then with those period, you will try to get maybe some lattice. I mean, I'm saying that it will work with certain conditions on the parameter of the differential equation. They have to be rational numbers or something like that.
The periods, like, okay, so what do you want for the, so
those periods will generate certain other varieties, I'm saying.
So I mean that, like for instance, this is an abelian variety, right? C mod gamma. Yes. So in general, if you have some other, like if you have objects which somehow you are working on, like Cn to the Cn mod some lattice. So for that, so you can do similar stuff, but but not all the
similar stuff. So that is what I'm asking. How this analysis that you told, how it generalizes, where it fails, all those sort of things. Anyway, so this was my curiosity. Anyway.
Okay.
So we can talk separately about it. So we will finish it because it is getting late here.
Okay.
Okay, see you.
So I guess I'll start with the representation point of view next time.
Thanks.
I spent too much time on the classical stuff. Okay.
Okay, see you.
See
you.
Nice. Bye.
I guess this generalization goes to tiling theory. There is a lot of work by Terence Tao, and there was a conference organized by Zekeli Hidi on harmonic and spectral analysis. And maybe one can see the website. And there are many talks on tiling theory, like this region, fundamental region determined by lattice, whether that tiles the system or not. And then that is related to the corresponding algebras and things like that.
Okay.
Thank you.
Okay, thank you. I will look into it. Okay, so we'll be closing it. It is getting late. So
Okay. I'll see you.